I'll try to wrap it up before noon. Let me start a timer so that I know where I am. Okay. So for today, I'm going to kind of, first of all, maybe in next 10 minutes or so, I would like to kind of give a refresher on what we have already done in the previous semester. I think most of you took this CT516 course last year. This lecture was held probably about almost 1 year and little more than 1 year back. But maybe some of you have taken it earlier than that. But regardless of that, I want to bring your attention to a particular technique that we looked at in this course regarding this modulation and demodulation method. And the way we said we will kind of look at all of the several modulation techniques such as BPSK, QPSK, Emery PSK, 16A PSK, QAM, and many such techniques is by generalizing what these modulation schemes are actually doing in a more fundamental manner. And essentially, we started looking at the modulation, specifically a particular modulated symbol as a vector in a vector space. And we looked at several properties of vector spaces. Then we looked at orthonormal basis of this vector space. And we said that if I have an orthonormal basis defined by this matrix capital E, and the columns of this E are the basis vectors. Think of them as essentially forming perpendicular directions. Then actually I can take any vector C and transform it to another vector V. And the good thing is that going back and forth between C and V is very easy because the inverse of matrix E is nothing but the transpose of the same matrix because of the orthonormality. And with that, we generalize that to not only vectors which are discretized in time domain, for example, but also to signals which are continuous in time. And we said that we can actually write any signal as a linear summation of these basis functions, Fi of t. And with that, we said that we will be able to represent a set of modulated symbols that we are transmitting, which is 1 out of capital M, as essentially a linear combination of this basis function. And Sm of I gives us the coordinates of the mth symbol. We actually said that if I have a symbol set which looks like this, there are 4 particular symbol waveforms, then I can consider 2 orthonormal basis functions, which are these 2 square pulses, and then write these 4 symbol waveforms as essentially coordinates defined over this basis function set. And they turn out to be nothing else but QPSK modulation. So F1 of t is the rectangular pulse defined like this. F2 of t is this rectangular pulse. And then these 4 signals then have this coordinate 1, 1, minus 1, minus 1, and so on. So if I put it on a constellation diagram, it gives me the diagram of a QPSK symbol. And so we said that QPSK can be actually any such waveform or any such set of 4 waveforms that can be represented like this. the basis functions can also be cosine and sines. And then we have the RF modulated QPSK symbols. We looked at some Gram-Schmidt procedure, which we don't need to get into right now. But the point that I think we want to remember is that a particular symbol is actually completely defined or characterized by its coordinates SM1, SM2 up to SM of capital K, where capital K gives the dimensionality of the vector space. There are a total of capital K different basis functions. And the modulated symbol is a linear summation of this basis functions. So this is a way of looking at the synthesis of the transmitted symbol waveform, the linear superposition of these basis functions, and that linear superposition is weighted by the coordinates of this symbol constellation symbol point along this k dimensions. And we said that because these basis functions are orthonormal, at the receiver, when we do the analysis function, all that we need to do is take the dot product of the received signal with individual basis functions. And the dot product turns out to have this particular block diagram when the signals are continuous in time. And so that is what we looked at. The synthesis happening at the transmitter, analysis happening at the receiver. And essentially, this basis functions, therefore, kind of getting cancelled out in some space, some sense. You are transmitting this vector S of M, and then you are getting it completely back in the absence of noise, because F and F Hermitian are inverses of each other. So this is what we had seen in the earlier class. I also want to spend just few minutes in looking at the optimal detection theory for this particular basis functions, where we said that we want to look at the conditional distribution of the vector R given that a particular vector S of M was transmitted. So we are now at this point. We are looking at this vector R. We have already kind of removed the basis functions from the received signal, and we got a vector back, R1 to R of K, in the presence of noise. And that individual element of that vector R is what is listed here. And then Sm of K is the coordinate of the particular transmitted symbol. And so therefore, this expression is the conditional probability of vector R given that S of M was transmitted and given that the noise is quite Gaussian. And we said that we want to maximize the a posteriori probability, which is Sm of Sm given R, probability of Sm given R. And we went over a specific mathematical procedure which gives us the map estimate of the transmitted symbol. It actually ends up having this particular formulation. And if all of these priors P of M are equal, then we get maximum likelihood rule, which turns into this. And then this we further simplified, I think. I don't know if I did this in this set of slides or later on. Well, yeah, it's here only. We said that error vector can be further simplified to this form, where at least we can get rid of R Hermitian R because it has no dependence on M. And so finally, we are ending with maximizing the dot product R with S of M, and then removing the energy, removing half of the energy of the transmitted symbol. And this dot product, we say it can be thought of as a correlation operation. So this was a very quick refresher on what we have earlier done. I believe you should have this slides with you, and I think I would like you to do this refresher yourself one more time, because now what we are going to do in today's lecture is we are going to take that modulation and demodulation theory, and we are going to generalize it. Okay, so that is the objective of today's session. Okay, this screen is visible, by the way.
Yes, sir.
Yes, sir.
Okay, so okay, so this is going to be a generalization of what we just very quickly went over. And I'm actually going to begin with the same topic of beamforming that we were looking at in the previous lecture. But then I'm going to look at a multiple access scheme called code division multiple access. My objective is also to bring in MIMO reception. I think I kind of ran out of time in preparing this set of slides, and so I haven't folded MIMO part here, but I will probably do it later on. But then what I want to show is that this beamforming, which actually is kind of similar to MIMO, so you can think of beamforming and MIMO kind of related as related topics. And then this code division multiple access is this new, completely new framework that we'll be looking at. So let us see, we will be looking at beamforming, that is one. MIMO, which is not here, but I will include it, which will be topic number 2, or rather I would say application topic number 2. Then this code division multiple access, which is completely different subject. That will be topic number 3. In CDMA, as of now, we will be confining to synchronous CDMA. But this mathematics that we'll be looking at is it is generalized to non-synchronous CDMA as well. And in general, what is this new technique which is touted as this 5G technique, non-orthogonal multiple access. So that topic of NOMA will kind of fall under bullet number 2. So let us see, we have 3 topics so far: beamforming, MIMO, CDMA, and then the 4th topic, which actually relates to not only communication theory, signal processing theory, but it also relates to machine learning and AI, which is the topic of deconvolution. That is the 4th topic, which again I have still not included here, but we will get to it later on. So there are 4 different application areas. They are different. The word different I want to emphasize. If you are focusing on NOMA, then you actually think that you are doing something which is different from beamforming. Or if you are, because if you are planning to expertise in computer vision and in computer vision or even in speech processing, in image processing, there is a problem of de-blurring the images or cleaning up the speech after it gets corrupted by echoes. So this different AI/ML techniques require modeling the blurring or the corruption or the distortion that is happening to the images or the speech, etc. It can be modeled as convolution of a clean signal, a clean image or a clean speech signal with some disturbances that get convolved with this clean signals. And at the receiver, the task is to recover the clean image or the clean voice, which essentially is deconvolution. In the context of communication receiver, that entire topic is known as equalization. So that is our topic number 4. So as of now, I'm looking at just 2 topics right now, but think that there are at least 4 topics. And these 4 are very powerful topics. They have, as I said, a vast domain of relevance and significance not only in the research community but also in the academics. Also in the industry. So these 4 different topics, we are going to unify them using a kind of a framework which will be applicable to all of these 4 topics. And then we are going to see some linear methods of dealing with the problem of extracting the information when we are in the midst of these different technical domains. Okay, so that is the plan for today. And it is in the context of this unifying framework where we will be looking at how to get some estimate of the information that has been received. It is in that context that I would like you to think of the entire technical concept that we will be going over as nothing but generalizing that modulation and demodulation mathematics that we just now went over. There we had some nice, clean basis functions that were all orthonormal because the definition of basis function was up to us. At the transmitter, we had complete freedom in defining those basis functions, and so we said that the best way to define the basis functions is to make them complete orthonormal basis set. In each of these 4 topics that I just now mentioned, we want to think of our received signal essentially as that linear combination of some basis functions, except those basis functions are now not necessarily entirely within our control. And so they may not be orthonormal. And so a lot of the research that is going on in all of these 4 domains relates to all the difficulties that arise when the basis functions are not orthonormal. But otherwise, if you keep that framework in your mind, that what I'm getting is essentially a linear combination of some basis functions, which then get additionally corrupted by the noise. And my goal is to do either the maximum a posteriori or maximum likelihood detection. Then you will be in a good position to leverage what we have studied in CT516 to this more difficult problems. In CT516, what we did was not easy. I wouldn't say it was easy at all. probably took a period of maybe 20, 30, 40 years before that nice mathematical framework was established that we looked at in CT516. But here, what we'll be looking at in the context of beamforming and CDMA, etc., will be, in a way, very much like that CT516 framework, but it is now more complicated. And that complication is coming only because the basis functions are not orthonormal anymore. Okay, so with that in the mind, let us look at the same exact signal model that we have been looking at in the previous lectures, where there is some symbol vector, S vector that we have said is getting transmitted by some total of k different sources, k different transmitters, and each of these transmitted symbols is being received with a particular either a temporal signature vector or a directional signature vector. In the context of linear time invariant systems, specific example we took was FIR filters. This WF0, WF1, WFK minus 1n, they form just the complex exponential vectors at this different frequencies. In case of antenna arrays, this WF0, WF1, they are known as the array vectors, and F0, F1 are the directional frequencies in the context of arrays. Who can tell me what is, for example, F1 in the context of linear array, uniform array? How did we define F1? In the context of linear array, we defined F1 as the direction theta1 from which the signal of the second user is coming.
Sir, it will be delay will be added over there, so it has to be e to the power minus j by 2 pi.
No, what you're talking about is this entire WF1n. That will be e to the power minus.
So F1 will be sine theta by 2.
Yeah, correct. So Divya is correct. F1 will be sine theta 1 divided by 2. We said that the spatial frequency is a sinusoidal function of the angle of arrival. So we have seen this model in the context of ULA, in the context of FR filtering, etc. And we said that the received signal can be written as WS plus U. Now, because I have already given you the clue, because I went over CT516 slides, you should not have a difficulty now, but otherwise, it takes a little bit of mental effort to look at this particular expression, WS plus U, and realize that it is actually analogous to receiving a symbol vector after it is modulated by the basis functions at a communication receiver. In CT516, this W matrix was formed by the basis functions. And so individual columns were nothing but the basis functions. And this S vector, what was this S vector in the standard modulation techniques?
K-dimensional S symbol vector.
Yeah, so it is K-dimensional symbol vector that gave the coordinates of the symbol point. So if I'm looking at a particular symbol of 8-array PSK, then okay, let me ask. So let's see. Komal, if I'm looking at 8-array PSK, what would be the dimension of S vector? Komal, are you listening? Please unmute yourself.
Hello?
What is the dimension? Yeah, what is the dimension of S vector when I am considering 8-array PSK?
And S is
Go
8-array PSK, you're asking.
Yeah, for 8-array PSK, what will be the form of S vector? Yeah, go ahead, Komal.
Yes, sir, I'm thinking. The form in the sense, a dimension of the vector you're asking.
Yeah, fine. You can say dimensions first.
So there are k elements in the S vector, right?
Yeah. So what will be the dimension of this S vector?
8,
8 dimensions.
8 cross.
8 cross 1.
Mhm.
Nidhi, what do you think, Nidhi?
8 cross 1.
Okay, Nidhi thinks 8 cross 1. Radhika, what do you think? Radhika, unmute yourself. What do you think? What will be the dimension of S vector for 8-array PSK? Yeah, go ahead, Radhika. Okay, Radhika is having some audio problem. Looks like Nemishi, it's your turn now. Are you there? If you are there, unmute yourself. You agree with Komal and Nidhi? It will be 8 cross 1.
So 8 cross 2?
8 cross 2. Okay. Anudeep, what do you think, Anudeep? 8 cross 1, 8 cross 2, we have multiple answers. Anudeep, are you there? Anudeep thinks it's 8 cross 3 for 8-array PSK. 8 cross 8. No?
Sir, 2 cross 1.
2 cross 8, sir, not 8 cross 8.
Okay. So Joel got it right. See, 8-array PSK is a two-dimensional technique. How many dimensions does 8-array PSK have? Just two, in phase and quadrature. Okay, so I think you all need to really refurbish your notes of CT516 and kind of bring yourself up to speed. Capital K, remember, is a number of dimensions, and so this S vector will be just it will be just 2 cross 1, and this W will be some matrix. The number of rows of W can be arbitrary. In fact, in CT516, we said that the columns of W are continuous in time. In general, they don't have to be, but in the labs of CT516 that you did, you probably had maybe 16 samples per symbol. And so then this W4 8-array PSK will be 16 cross 2. S will be 2 cross 1. But there will be 8 such S vectors for 8-array PSK because there are 8 symbols. Is it fine? It may take some time for you to wrap your arms around this unification that we are planning to do, but now remember this S is always a vector. It is never a matrix like what Nemishi or Anudeep are thinking, because this X is also a vector. But in a way, this answer that S is a matrix is maybe kind of okay because S vector can take, for 8-array PSK, it takes one of 8 different possibilities. These are the 8 symbols. And so if I put those 8 possibilities side by side, then I get the constellation diagram for 8-array PSK. Now, over here, in this model that we have seen earlier for FR filtering or for beamforming, this x0, x1, xk minus 1 are obviously now not samples of 8-array PSK. Okay, by the way, given that most of you, probably all of you other than Joel, struggled with this question, please take a look at what this 2 cross 1 vector will be for different symbols of 8-array PSK. What will it look like? And I'll give you the answer actually, that for the first symbol, the 2 cross 1 vector will be coordinate of the first constellation point of 8-array PSK. And if that constellation point is on the horizontal axis, then the S vector will be just 1, 0. Right? The second vector S for the second 8 PSK symbol, it will be what? Who can tell me that now? Bhavesh, you haven't spoken. Can you tell me what will be the S vector for the second 8 PSK symbol, the second symbol of 8 PSK constellation? I already told you first symbol is having vector S, which is 1, 0. 2 cross 1 vector, 1, 0. What about the second symbol? Bhavesh, you are there, unmute yourself.
Yes, sir. The first vector is 1, 0. So 1, 1.
Yeah, okay. Joel kind of gave the answer. Joel, maybe if this was an exam, you will be caught as helping Bhavesh. But yeah, so the answer is 1 over square root of 2, 1 over square root of 2, because the second symbol of 8 PSK is 45 degrees from x-axis. So its constellation point is 1 over square root of 2, 1 over square root of 2.
So only you could see my answer.
Oh, okay. Okay, so then that's good. Arushi, what about the S vector for the third symbol of 8 PSK?
Sir, it will be 0, 1.
Yeah, 0, 1. So I hope that you are on the same page now. All of us are on the same page. So that is how we define the modulation framework in CT516. But in this generalized viewpoint that we are now taking, the individual element of this vector S actually are symbols transmitted by k different transmitters. In CT516, all of these k samples are generated by the same transmitter, because it is the same transmitter which is sending out 8 PSK. And secondly, the individual elements, this x0, x1, xk minus 1, they are all real value, because we have considered, for 8 PSK, we have considered the two perpendicular dimensions as two column vectors. And so these samples of S vector are all real value. In this generalized viewpoint, this x0, x1, xk are actually now the modulation symbols themselves that are being transmitted by different transmitters. And if we confine ourselves to only Emery PSK or Emery QAM, we don't get into orthogonal modulation, then we have seen in CT516 that those Emery PSK or Emery QAM symbols can be considered as complex valued numbers. And so this x0, x1 are now complex valued. And they are generated not in a co-located manner. They are not generated by the same transmitter, by the same FPGA. X0 is generated by one transmitter located at one place. X1 is a complex valued number which is generated by some other transmitter, which may be like 100 kilometers away. And so those are the two changes. The first change is mathematical in nature. The real valued samples of S vector are now replaced by the complex valued numbers. The second change is in terms of practical implementation or the overall system architecture. The modulated vector S is generated in a co-located manner, whereas in this context, these X samples are not necessarily co-located. And when they are not co-located, the biggest implication is that there will be different channel impairments. These different symbols will go through different delays and different Dopplers. And so that is where the synchronicity comes into play. Whether we can assume that the QPSK symbol X0 transmitted by the first transmitter has been synchronously received with, let's say, 8 PSK symbol X1 transmitted by the second transmitter. Whenever that is applicable, we can actually write the same equation number 2. When the synchronicity is not there, then we have to be a little more careful. We can still come up with some equation which is like equation 2, but it becomes more complicated. Now I will ask this question to who has not spoken. Kishan has not spoken. So Kishan, let me take an example that there are two users and they both are transmitting two PSK symbols. And how many possibilities can there be for this vector S?
So like 2 users and 8 PSK symbols.
Yeah.
Okay. So
First of all, what will be the dimension of the signal?
10 cross K.
Yeah, so what is the type of dimensionality that I am looking at? I mean, that is easy. I already told you 2 users, so capital K is 2.
2. Yeah.
So now we are looking at a two-dimensional space. And the two dimensions are formed by this WF0 and WF1.
Yes.
I'm asking you, what is the number of possibilities of this S vector?
8 and 8. There's 16 possibilities.
16. What do you think, Soumya? Soumya, are you there?
Two possibilities.
Two possibilities.
No, sorry, I don't know.
Even if there is one user, there is four possibilities. Two PSK
Oh,
is four.
okay. Sorry, sir, I don't know.
So for QPSK, it is like 8 possibilities.
QPSK, it is 8. QPSK is only 4.
I mean, like 2 users and QPSK.
Yeah.
So, like at one time, I will get QPSK symbols, 4 of them from one user. The other will be zeros.
Why
So
others will be
then
zeros? Wait. Why others will be zeros? When one user is transmitting x0, can that user say to user 2 that, oh, you transmit 0? The first user cannot say that.
Yeah. Okay. I think.
Okay, I had some answers on the chat window. Let us see. Divya, what do you think? Bhavesh said 8C2. Joel said 4C2. No.
4C2, sir. 4C2.
No. Those are not the correct answers. Who has not spoken yet? Okay. See, actually what Kishan said first is the right answer. This x0 can take 4 possibilities, right? Because it's QPSK. And x1 can also take 4 possibilities because it is QPSK of the second user. And these two users are not, I mean, they are independent users. So they can transmit any symbol anytime. They don't worry about what the other user is transmitting. And so for each of these 4 QPSK symbol, there are 4 possibilities of x1. And so you will see that there are a total of 16 possibilities of vector S.
Sir?
Yeah.
Sir, yes, sir, as opposed to the previous case when we were comparing these to be bases and the constellation points.
Yeah.
Okay. So if we are considering constellation points, then the S vector will have only real values.
No, we are considering this to be what is known as complex vector space.
Yes, sir.
So
Sir,
the dimensions of the axis. Bipin, there is a lot of background noise. You can mute yourself temporarily. So, yes, in CT516, these basis vectors were all real value. Like what Bipin is pointing out, now these basis vectors are complex value. And so it is not possible to kind of visualize this as orthogonal lines anymore, because these lines are actually now complex value. I mean, it is not possible to draw them on a two-dimensional paper, but still it is possible to visualize this WF0 and WF1 as forming, let us assume that WF0 is perpendicular to WF1. If I take dot product of the two, the dot product is 0. Then I can imagine that WF0 is a horizontal dimension and WF1 is a vertical dimension. So I have to kind of further abstract out my visualization, but the bottom line remains that I have two perpendicular dimensions And on each dimension, I am sending 4 possibilities. And those 4 possibilities are independent of the 4 possibilities that I'm sending in the other dimension. And so I get a total of 16 possibilities. So in that context, let us look at what we saw last time. In the SMUX MIMO example that we looked at last time, it is those antenna vectors H1 and H2 which were forming our basis vectors. But those were also complex values. But that time, I think we all agreed that if those antenna vectors, the columns of matrix H, if they are orthogonal, then I can put them on 2 perpendicular dimensions. And I said that if each antenna is transmitting 2 PSK, then in SMUX MIMO, there are the 16 possibilities. So using these 2 antennas, I can transmit, oh, screen is blank, sorry about that. Okay, can you see the screen now?
Yes, sir.
Okay, so remember that last time we said that in the MIMO, if I consider this individual channel vectors to be orthogonal to each other, then for a case when there are 2 transmit antennas, just H1 and H2 are present in the H matrix, then I can draw the constellation diagram of these symbols that are being transmitted by this MIMO. Hello? Pankit bhai, I will call you back, okay? In just 5 minutes. And so that is why we said that SMUX MIMO is so powerful. With 2 antennas instead of 4, I can transmit 16 symbols. I can get 4 bits of information out instead of just 2 bits. And so on. If I have 3 antennas, then how many bits of information can I get out if I transmit QPSK on each of these 3 antennas? $64, yes, Pavesh, yes, correct. The reason it is 64 is because when the 3rd antenna is present, I will draw 1 dimension like this. I'll draw
In 3D.
I will, yeah, in the 3rd dimension. And then this tile that I have put here, it will become a 3D cube. And there will be a total of 64 points within the cube. So I can transmit 6 bits of information, log base 2 of 64. So this is what we did last time. Today, I did exactly the same thing, and I didn't expect that it will throw you off. But this is essentially the same thing that we have done in the context of MIMO. The only difference is that the notations have changed. In MIMO case, I call WF0 as H0 for H1, and this WF1 as H2. But otherwise, apart from the notations, it is the same situation. Oh yeah, one other thing in MIMO is that synchronicity is easier to guarantee because these different transmitter antennas are typically physically co-located. Whereas in case of this beamforming type of situation, this x0, x1, they are different users, not co-located, and so it may be difficult to ensure synchronous reception. But if we assume that they are synchronously received, then this framework is same as that MIMO framework that we saw earlier. Is this fine? Bibin?
Sir, I understood. I think I think they couldn't answer that because there was some confusion. They're still thinking about xn0 and xn1 as scalars.
They are scalars.
So actually,
No,
xn0 and xn1 are complex numbers if you are considering QPSK, right?
Yeah, but they are complex valued scalars.
Yes, sir. Yes. Sorry, I meant the real numbers.
Right. Okay, fine. So I have about 5 minutes left. So let us move forward. So now with that model, we are saying that what the receiver is going to do. So let us assume that receiver is operating in real time, meaning it doesn't have any prior information, and a particular vector x is observed at the input to the receiver, and we are now focusing on what the receiver will do in terms of. Remember, the title of this talk, this lecture is generalized demodulation. We already saw how the conventional QPSK or 8PSK receiver will receive X, and from that it will figure out this vector S that we have seen earlier. All that it does is it multiplies X by W Hermitian. And because W is orthonormal, we get a perfect cancellation, and we get essentially vector S with some noise. Now we are saying that this W is not necessarily orthonormal. Okay, this kind of we already talked about. So there are two views of looking at this particular model. One is that our received signal is a composite of k source signals, where each of this transmitter is interfering with the other. That is one view. And if we take that view, then this generalized demodulation, we would call it as interference cancellation. But the other view is what we just now talked about, that what we are getting is essentially a supermodulation. Essentially, different users are transmitting information which is modulating these different basis functions, WF0, WF1, etc. And so now we can say that what our receiver should do, what the beamformer should do, is essentially a generalized demodulation operation. Okay, so all of you would have heard of this beamforming, and some of you have actually already started working on beamforming. But what I wanted to give you with this is a kind of a, I wanted you to take a step back and look at what we are actually doing when we say we are doing beamforming. Okay, so in the most abstract mathematical sense, what we are doing is essentially demodulation operation. In a lot of papers that some of you, for example, Arushi, maybe Komal, and others have looked at, this is also known as source separation problem. That source separation is another way of looking at this problem from this first view. Okay. Now let us assume that using the techniques that we have seen earlier and the techniques that you are exploring as part of lab 3, let us assume that in the frequency of arrival for the temporal case and direction of arrival for the spatial case, we have estimated them. Maybe we have used MVDR, maybe we have used music, maybe we have done simple power spectral density estimation. But once we estimate this FOA or DOA, we can say that we can formulate the columns of matrix W. And so now our goal is to be able to do this generalized demodulation. The last thing that I will do today, my timer has ended now, so I won't take too much time anymore. The last thing I want to do today is that, remember, we have already looked at this correlation matrix of the signal that we have received, which is XX Hermitian, and it takes this particular form that you have investigated as part of lab 2. Now I want to define one more correlation matrix, and this time it is the correlation matrix of this W. And the way I'm going to define it is that it as W Hermitian W. So my question is, what is this matrix W Hermitian W in the context of CT516? Who can tell me that? In CT516, what was this W Hermitian W? Or in general, let us say we are back to the traditional modulation schemes, 2 PSK, 8 PSK, 64 QAM. For those techniques, what will be this W Hermitian W? Bhavesh?
So projection.
No, I'm saying what will be its form? What will it look like? Huh? Your voice is not clear. Arushi? Yeah. Bhavesh, yeah, you are not audible.
So now is it audible?
Yeah.
So I'm saying that it can be related as a projection of basis vector.
Yeah.
On the
but
basis
what will be
vector.
this? Yeah, exactly. But then the result,
Yeah.
this R, what will this matrix R look like?
It will have diagonal elements. If the basis vectors are orthogonal and orthonormal, the diagonal element should be the having a magnitude of 1, whereas the rest should be 0.
Exactly.
Yeah.
And there should not be any need of saying that if they are orthogonal or orthonormal, because they are orthonormal.
Oh, sorry. Yeah.
In CT516, all that we considered was the case when basis vectors were orthonormal. So in
Yes.
CT516, this R is the identity matrix. That is what Bhavesh does not say. But other way to look at R is that it is different elements of R are defining the correlation between different columns of W. In case of orthonormality, each column of W is perfectly correlated with itself. That is why you get 1 on the diagonal. And it is perfectly orthogonal to all the other columns, so you get zeros. But in this generalized case, this R will not be necessarily a diagonal matrix, because the correlation of one column of W with the other column of W will not be identically 0. But still, what we hope to get is that R looks sort of like diagonal, meaning that the elements on the diagonal are very strong, and the elements away from the diagonal, the off-diagonal elements, are smaller than the diagonal elements. Which is another way to say that the correlation between different columns of W, we want it to be small. Sometimes it is small, but sometimes it is not. In case of direction of arrival or frequency of arrival, if I am considering two vectors WF0 and WF1, where F0 and F1 are very close together, then the correlation between them will not be small. In fact, we went over a formula to determine what that correlation value will be. Essentially, any particular element of this R matrix, what will it be? What is that formula? In case of
So that small RL.
no, I'm saying a specific formula when we are looking at uniform linear array of the model, or when we are looking at this FIR filters whose impulse responses are DFT vectors. Then the correlation between WF0 and WF1 is given as
Summation AK square into e raised to j2 pi k.
And then we solved that summation.
Yes.
What was the answer we got? I said it is the most fundamental equation of signal processing.
So sinc function.
Sinc function.
Yeah.
So in case of this uniform linear array, or in case of this DFT filters, this R elements of R are completely determined by that sinc function. And you know that if I am sampling the sinc function very closely together, then yes, the diagonal element I will get is 1. But the off-diagonal element may be as large as 0.99 if the second frequency is super close to this actual, the main frequency. And so we cannot always hope that this R will be looking like a diagonal matrix. So this is where we will end today, and we will take this up on Wednesday. See you that time. I mean, unless if you have any questions, I am available.
Sir,
Let me stop the presentation.